blanket over his head and refusing to take milk interrupts. So enabling and disabling interrupts is a fundamental facility. And also the processor ignoring interrupt requests is also very important. So the processor should be able to say, I am not going to take any interrupts. So enabling and disabling are that also. Now, this is not so intuitive that enabling and disabling interrupts should be both at the processor and at the IO side. So definitely a processor can say, I won't take interrupt requests, but the IO device itself can also say that I am allowed to raise requests only when something is set to 1, or if something is set to 0, I am not going to raise a request. So this also is possible. You can do it at the processor end, you can do it at the IO end. Right? So since the control word of the IO is in your hands anyway, so even the processor can write this bit on the IO end. So we agree that the enabling and disabling of interrupts is an important facility. For instance, look at these interrupts. So the driver rings your doorbell, driver rings your doorbell and asks for the keys to the car. So what do? If this happens, you know that the car keys in every house are kept in a particular place. So you go there, you unhook the key, you come to the door, you give the key to the driver and you close the door. And he does whatever he wants to do with the car. Fine. So that's a very specific task. If the driver asks for the keys to the car, you don't go to the fridge and make a sandwich and give it to him. You don't do that, right? You go to that place and you get the keys of the car. So it's a very specific thing. Now, what if that usual way in which the interrupt comes from the door, somebody calling from the doorbell, is not an usual way? For instance, suppose at 2 o'clock the thief knocks on the window and says, give me your house keys. Now you know that you will go from the window, go to the almirah, get your house keys or your jewelry or your property documents to your land, and you will come back to the window and give it to him, isn't it? You will not go back to the door and give it to the thief. You come back to the window. So the location of this interrupt is from the window. So you know this is a sort of thing. So the moment you get a knock on the window, you immediately say, oh, that's a thief. He must be asking for my house keys. So you know what to do, right? So you can actually distinguish between the driver and the thief by saying, okay, the driver will never knock on the window, right? The thief will never knock on the door, right? So that's a locational identification of the interrupt. Similarly, the milkman asks you to take a milk delivery. Right? So he has the milk in his hand. He says, are you ready to take the milk? Come take the milk. So then there's a fixed set of actions to be done. A particular milk can to be collected, washed, brought to the door, milk to be poured in, and then the door to be closed, and you come back and give the milk in the kitchen. Right? Now, there is no way in which he can initiate this milk delivery and you don't take the milk. You have to end it by taking the milk. But there could be an option. For instance, the vegetable cart seller shouts, do you need vegetables? Now, if you don't respond, then you don't need vegetables. Right? So that sort of interrupt is like a question that if you want, you can be interrupted. If you don't want, you don't get interrupted. Don't buy vegetables. He's going to go on shouting and he's going to walk along the street. If you want vegetables, you go, you call him, say, come back, sell me vegetables, and then proceed. Right? Sometimes the entire sequence of action is not pre-known. For instance, electrician asks if all devices are switched off in the house. Right? Whatever he's going to do, he wants everything switched off. Now, everything switched off means that you know where everything is in the house. If you're going to search, then there's a slightly fuzzy aspect to this as to where are the switches to be switched off. So you have to find that out. That takes more time. So that's another type of interrupt. Right? Then there is an interrupt in which there is nothing to handle. Like for instance, this Sansani fellow says, bearded fellow says, Shabdhan ho jao, ye ho sakta hai. Be careful, this could happen to you. After that, he says nothing. What could happen to you, you don't know. Whether you are going to have an accident or Osama bin Laden is going to bomb you, all that is not said anymore. He just says, beware, this could happen to you. So you are generally aware, but there is nothing to be aware of because he says nothing more. So that is also an interrupt, right? Now, all of these qualify as interrupts, but if you look at microprocessors, computers in general, you will see that there are two types of interrupts. One is this, handling an interrupt from one device. The other is handling interrupts from many devices. Now, if you look at the first problem, handling the interrupt from one device. You remember what I said yesterday about um, somebody tapping your shoulder. I qualified that tap on the shoulder by saying, okay, instead of just tapping the shoulder, which may or may not actually catch your interest, so what if you place your hand on the shoulder till I look at you? So when the device activates this interrupt request signal, that's like placing the hand on the shoulder, it keeps the signal activated. It keeps the hand on the shoulder until I look back at it, until the processor accepts that request. Right? So the processor has to say, yeah, I feel your hand on my shoulder. What do you want? So there has to be a, I want this question. There has to be a, what do you, okay, I now acknowledge you. What do you want? So there has to be these two components to this placement of the hand on the shoulder. That means this interrupt request signal will remain active during the execution, right? Till something happens, till it knows that the ISR is handling me. And you must also say that, okay, that particular active request should not be serviced twice. For instance, if your hand is on the shoulder and I am trained to say, yes, what do you want? And your hand continues to be on my shoulder, I will keep on saying like a moron or a parrot, whichever charitable way in which you want to interpret it. I keep on saying, yes, what do you want? Yes, what do you want? Yes, what do you want? Right? If I keep on doing that, it leads to a loop because you are going to keep your hand till I service you. So there must be some way of saying, okay, I have said an inter once, or I've given a interrupt acknowledge once. I'm not going to do it again. It's the same hand on my shoulder. Right? So the other way is that the processor automatically disables interrupts. Let me put on my laser pointer. Right, so laser pointer. So the processor automatically disables the interrupts before it starts the interrupt handler, which means does a little bit of saving of the program counter processor status register, saves the contents of the processor status register with the interrupt enable equal to 1. Then the processor clears the interrupt enable in the process status registers, which means no further interrupts. Then it begins interrupting of the service routine. When it returns, the process status register is restored, setting the interrupt enable back to 1. So you can again interrupt the process. So while it is doing something, it doesn't want to be interrupted. That's the general principle. Right? So if you summarize what we said here, you get something like this. First, the device raises an interrupt request. This is one device, not multiple devices. Multiple devices are coming. So the device raises an interrupt request. And the processor interrupts whatever it is doing, saves the PC, saves the PS, disables the interrupts so that recurrent interrupts don't happen due to the same pin, clears the IE, sets it to 0, no further interrupts. Action requested is performed, the handler routine is invoked. After that, the device is told your request has been recognized, and that really means that you can take your hand off my shoulder. So it deactivates the interrupt request signal. If it keeps the interrupt request signal activated, then the moment I turn on the enable interrupt, I will again say, oh, you still want something? What do you want? So that is not, if it is not true, the interrupt request signal should be deactivated. Once you complete the handler, restore PC and PS and resume the interrupted program. As simple as that, right? But it needs some provisions to be made inside the computer for all this to happen. But it gets a little bit more complex if you have more than one device, right? Now, first thing is, how many more devices? The answer is reasonably more devices. I mean, two, of course, is more than one. But when we provide for interrupts, we don't only think that there are going to be two devices which will interrupt. So we think, okay, there may be 30, maybe 50, but certainly there will not be 64,400 and 536 devices. Nothing very arbitrary in these numbers. So wherever we draw that information from, experience, from the number of interrupts we typically encounter, we say that, all right, if you give 10 interrupts, 10 devices, if you can handle their interrupts, that's more than enough. Now somebody may say, no, 20 is not enough, 32 is enough. Somebody else may say, no, 32 is also not enough, 256 is enough. But at some point, even with such debating, you will reach a number which is reasonably good, and for most purposes, it will be okay. You will never encounter so many devices, so you keep a higher number, and then you proceed on that operational principle. Second thing is, these devices are independent. Whoever is interrupting, there is no relationship between the interrupting devices. So there is no particular order in which they will generate that interrupt. Anybody can interrupt at any time, right? So X may request an interrupt while you are servicing the interrupt for Y. Or several devices may interrupt at exactly the same time. So how does the questions which come out are, first, how does the processor determine which of these 10 or 32 or 256 devices, or whatever number you have decided to service, which of these devices is requesting an interrupt? Secondly, each of the devices is likely to invoke a different service routine, right? A separate service routine for each of them. So how does the processor know which service routine for which interrupt? That's the second question. Then should a device be allowed to interrupt the processor while the other interrupt is being serviced? So should a device be allowed, this is the case here, while another interrupt is being serviced, right? And then lastly, what if they contend? What if two interrupt requests simultaneously happen? Now simultaneous means at the same time, right? But from the processor's point of view, it means in the same T state, right? So anywhere between the T state, and you know that a T state is something like this, right? So if you have a T state which is like this, so whether I interrupt here or I interrupt here, it counts as one T state. So anywhere in this is considered simultaneous, right? So if you have two such simultaneous interrupts, how do you handle? For instance, you cannot say that this one is later than this one, so I should take this one first. From the point of view of the processor, both of them have occurred at the same time. In the same T state means at the same time, because they are anyway going to start executing at the instruction boundary when the instruction finishes. Right? So that is the understanding which we operate on. Let me switch off all ink. Okay. So these are the questions, and these are the questions which the processors and the computers actually handle through their mechanisms. Now, how do you identify the origin of the interrupt? Right? For instance, you had two interrupts. One was the thief at the window asking for your house keys. Other was the driver at the door asking for your car keys. Right? So one of the ways in which you can service these two, thief and driver, is run from the front door to the window. See the thief is not there, run back to the front door. See the driver is not there, run back to the window and check if the thief has come. Thief did not come, go back and see if the driver has come. This is polling. You keep polling the front door, polling the window, and whoever you find first, thief or driver, you hand the right key to the right person. Right? Of course, I don't know. If you hand your house keys, I don't know what good it is to hand your car keys to the driver. The house keys will contain the car keys. So anyway, that's another question. So in without realizing it, I think the thief is a higher priority interrupt, because if he takes the house keys, it's no point saving the car. Right? You're not going to be able to access the car. Anyway, if you poll, that's very simple. It's easy to implement. Only disadvantage is you spend a lot of time polling. You run from the door to the window, window to the door to the window, window to the door. Right? There is an alternative. Right? So this is the alternative. Okay. My laser pointer is not here, so pointer options. Okay. When an interrupt request is received, first, where did it come from? Who is the device who raised that request? Right? That's the first question to be answered. If two devices raise the interrupt request same time, we must be able to say which one we are going to service first, because the processor is a sequential machine. It can only service one of them. So there's no point saying 50% to this and 50% to that. It doesn't happen. One has to go first, one has to go next. It must be possible to break the tie. So how the processor will break the tie, we will see later. When the interrupt service routine for the selected device has been completed, the second request can be serviced. Now, what is the information you need? The information which you need to see which device is requesting an interrupt is available in its status register. So it raises a request and simultaneously it sets to 1 a bit in the status register. You know that every device has a status register, a control register, and a data register. We know that from the basics of IO devices. So in its status divisor, it will set that bit to 1, saying I am the device asking for an interrupt. So then what you do is you poll it. You poll the status registers and say which device has a 1 in its status bit. So the simplest way is identify this device by poll all IO devices. Right? And the first device you encounter with the IRQ bit set to 1 is the device you service. Right? Now, is this fair? Not necessarily, because if you do this, then it depends on in which sequence are you polling. Because if you poll a particular device early and it sets its IRQ, it will always receive service, whereas the devices later on in the polling sequence will never receive that service. So that it's not fair, but it's one way. Right? So let's look at the second part. That is, how do we use what are called vectored interrupts? So for vector interrupts, these have interrupt handlers which have definite addresses. See what your textbook says about it. To reduce the time involved in the polling, so you want to reduce this polling to 0. So a device requesting an interrupt identifies itself directly to the processor. Then the processor starts executing its service routine. Whichever device identified itself to the processor, there is a known service routine which the processor will execute for that device. So the term vector interrupts refers to all schemes based on this approach. Now, how does a device requesting an interrupt identify itself? Number one, it has a dedicated pin. For instance, if you get a knock on the window, then you know it is the thief. If you get a knock on the door, you know it is the driver. So there is a dedicated pin for the thief, a dedicated entry point for the thief. There is a dedicated entry point for the driver. Depending on which one you hear the knock from, you can make out that is the thief device, this is the driver device. But then if you try to mimic this in a processor or in a computer, it means you need to have 2 pins or 3 pins, or if you want 256 interrupts, you need 256 pins, because each device will have its own pin. And that's how you identify the device, right? So the dedicated pin approach is very expensive in terms of pins, right? Did you understand what I said by meaning very expensive in terms of pins? Was that phrase easy to understand?
Yes, sir.
Too many pins is bad, isn't it? Uh, Too many pins means an initial cost to the manufacturer. Fine. Because you know and I know that if I have a, okay, if I have a IC, the length and the width of the IC is to be kept small. Of course, when you see an IC, inside the IC, the silicon is only this much, right? So if you have pins on this IC like this, right, a very rough set of pins, right, there is a wire inside the IC which is soldered from the central silicon chip to the body. But even so, suppose you say that I'll have 256 interrupt pins. What you're saying is my device will be like this, and I will have 1, 2, 3, 4, up to 256. Right? Now, if I ask you the question, are you so sure that wherever this device is going to be used, there will be 256? Or are they going to be maximum 256 devices, but typically there will be 4 or 5 devices? Now, if your answer is, well, typically there will be 4 or 5, but at most there will be 256, then such a thing is a very expensive decision to make. That you have placed 256 pins, you have made the IC maybe 6 times its original size, but you are using only a very small fraction of the pins. So that's not good from the manufacturer's point of view. The package is bigger, it's difficult to handle, difficult to solder, right? It occupies more space, it cannot the wires inside are longer. All of these are extra costs, right? So we don't like this. We don't like having dedicated pins, right? So just put yourself in the sorry, I'll just erase these things. Okay. Put yourself in the position of a committee in the 1970s, 80s, who is designing a microprocessor and deciding how many vectored interrupts, how many pins it should have. So the committee will say, okay, let's not have 256, let's have 2, let's have 3, let's have 4, let's have 5, let's have 6. Somebody says, no, 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 we must have 32. Okay, let's have 32. So it's like that, fine. There is, of course, another way. The other way is that the device which is interrupting tells the processor that where is my ISR or where is my handler? Like the milkman rings your door and then tells you, get that milk bartan from inside. So even if you are Sushant or your Sushant's uncle or your Sushant's sister, you will still know because the milkman himself is saying, do you see that milk vessel hanging in your kitchen on the rack number 2? Get that. So you have no problem. Oh, he told me, I'll go and get that vessel and give it to him. We'll put the milk in it. And that's what. So the device itself is saying to the processor, I am going to interrupt you and I'm going to tell you where my interrupt handler is. So there's no problem. Now, instead of the doorman, suppose a petrolman comes from the petrol pump and says, I'm going to give you petrol. The petrol can is kept in the outhouse in a metal canister. Go get that. Now you will go to the outhouse and get a metal canister. You will give it to him. He'll fill petrol in it. Right? Now do you see that even though they are all interrupting from the door, each person who's interrupting is telling you what to do. So that's the second principle. You don't need a different pin for every interrupt, but on the same pin, the different devices will tell that, okay, I am device number 67, go to this interrupt handler and do this for me. Well, that's wonderful because then they all can share one pin. All you have to ensure is one device on that pin. That's all. So really speaking, if you have this second way of handling an interrupt, you can have 32 or 256 or 16 or 8 or 2 or 37 or 64 or 127. It does not matter because each device is going to send a special code to the processor, right? Through the, of course, Professor Hammersher is a very coy, he uses words very coyly. He says through the interconnection network. What he means is that it sends it through the bus, right? So wherever Karl Hammersmith says interconnection network, just substitute in your mind the word bus. So through the bus, it sends a special code. Now, just these two, without me explaining anything more, which I'm going to do, just these two things, are these clear?
Yes, sir.
Yeah, so there are two ways. One is dedicated pin for every interrupt, very expensive in terms of pins, needs a lot of pins. And the second is same interrupt pin, but on that interrupt pin, different devices give you different interrupt handler scheme addresses. So you can go to that interrupt handler. So saves on a pin, saves on many pins. You can dedicate one pin, right? And you know, if some committee member still has some misgivings, there's only one interrupt is just too few, then you can say, just to keep you happy, let's give a few interrupts which are location based. Let's say we have 1, 2, 3, 4 pins. Right? Are you happy with 4 pins? We say, yeah, 4 pins is fine. But 4 dedicated pins and 1 pin on which you can do the second thing. So you have this and you have this. You don't have 256 of these. You have 1, 2, 3, 4 of these, or 5 of these, or 16 of these, or 32 of these, but not too many. But mostly it is this. So then all the entire committee is happy. Okay. Now, if you do this, one scheme is have a portion of the memory in which the addresses of the interrupt service routines are kept. Fine. So that particular portion of the memory, right? These addresses, of course, are the vectors themselves, right? And this portion of the memory is called the interrupt vector table, right? So it's like this. If I can draw it, okay. Let me draw it using a fine. So what I'm saying is that I have a portion of the memory which is like this, right? And in each of these locations, let me just designate these by locations. In this, I have the address of the first ISR, right? And then I have the address of the second ISR, so ISR 2. I have the address of the ISR 3. And when I get the first device, it comes to this, it examines this, and then it jumps to a portion of the memory where this ISR is there. Now, when it's the turn of the, let's say, second device, that will come here, find out this address, go and execute that interrupt service routine, and then come back. So this particular part of the memory is called the vectored interrupt table. So we have a table of addresses, and each device has its own dedicated address. And we must, of course, then have a way of finding out which device. But that will come later, right? So let me go back to this. So we have a vector table, and we have a set of interrupt vectors. For instance, you have 128 bytes of memory, which holds a table of 32 vectors. 32 means each vector is 4 bytes. So for 32 vectors, you will need 4 into 32 is 128. Now, interrupts may be numbered. Let's say 256 interrupts, so 0 to 255. Right? This 255 does not have anything to do with this 32. Right? This is another line. Right? So if I had 128, then I would have 32 interrupt vectors. But suppose I had 255 interrupt vectors, right? Then I could have I could have it. What the point is that there is nobody preventing me from having 256 vectors in that vector table, or 32, or 16, or 8, or 4. That is my design consideration, right? For example, in 8085, it's a little different, but in 8086 and upwards, there are 256 interrupt vectors. The first five interrupt vectors are identical to all members of the Intel family from 8086 to the Pentium, right? It's different from 8085, 8088, but 8086 upwards, everything is common. Then each vector is 4 bytes long and contains the starting address of the interrupt service routine. And typically this interrupt vector table is in the lowest address range, right? But the locations of the ISR, these locations, this and this, right? They can be anywhere in the memory, because where you jump to, right? Where you jump to is not defined, right? This can be actually anywhere in the memory. So that's what is being said here, that the interrupt service routines may be located anywhere in the memory. When the interrupt request arrives, the information provided by the requesting device is used as a pointer into the interrupt vector table, and the address in the corresponding interrupt vector is automatically loaded into the program counter. So execution jumps to that particular ISR. If you look at, for instance, the 8085, because that's what we have been looking at, you'll find that it has 4 pins, right? Now, how do I find those 4 pins? Where do I go and learn this information? Of course, I can look at a textbook on 8085, but I choose to look at, let's say, the 8085 data sheet. Hope I'll find it. I am not finding it. Okay. If I'll find it, let me see. Okay, yeah. So this is the 8085 data sheet. So this is from Intel. Last time we had pulled out one data sheet, I think of 8279 or something like that. And now I'm pulling out the data sheet of the Intel 8085. So just look at the data sheet. Do you read data sheets?
Online modes are not so much.
Hmm?
Simulators, we are mostly using simulators. So
Why don't you read data sheets? You know, it's like reading the Bhagavad Gita and reading Chidananda's interpretation of the Bhagavad Gita. So you would rather read the Bhagavad Gita itself than read what Chidananda says about the Bhagavad Gita. So when you read your textbook and what it says about the 8085, why not go to the mother of the 8085, Intel, and download the data sheet and read the data sheet? Very often, we don't do that because data sheets look so hairy. You know, if you look at a data sheet, it doesn't look friendly at all. Right? Just look at this; it's full of things, right? And so many things out of these we don't even understand what this means, right? But the trick is to learn to understand. So if we read along in the data sheet, I think there is nothing more authoritative or authentic as a data sheet. So anytime you have an IC, don't ask for a guidebook to that IC. Ask for the data sheet to that IC, because that is the definitive thing about the IC. There is nothing else known in this world other than what is written in the data sheet. Right? So whether it's Carl Hamisher or Smriti Sarangi or it's Hennessy Patterson, they will take the data sheet and interpret it for you. Why not read the data sheet directly? So let's look at the data sheet. Right? Number one, let's forget this for the moment because we are not looking at the power considerations in the 8085. Right? And let's look at this. 4 vectored interrupt inputs. 1 is non-maskable. Right? There is a serial in serial output, which we are not looking at the moment. Let's look at these 4 vectored interrupt inputs. Let's see if we can identify these. Now, naturally, when we look at the pinout of the 8085 and we read, right, X1, X2 is typically a crystal oscillator input, a reset, a serial output, serial input, then something, 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 something. Doesn't look like anything we have seen anywhere in our digital electronics, etc. Trap doesn't look like anything we realize we have seen in digital electronics. So let's put trap aside and we'll come back to you later. RST 7.5 doesn't look like anything we have read in the latch, AND gate, OR gate, XOR. Let's put it aside. RST 7.5, 6.5, 5.5. Then INTR, inter. Inter sounds like interrupt. Right? So let's mark it something related to interrupt probably. Right? Then INTA. Okay. Anybody who has done Sanskrit or is from Andhra Pradesh can do a Sandhi Vichhed on this and say INTA looks like acknowledge to int. So int acknowledge must be INTA. Fine. So, and it is so close to interrupt, the coincidence is too high. This must be interrupt request, this must be interrupt acknowledge. If it is not, I'll correct myself, but at the moment, let me go ahead with this thinking. Okay? Fine. What does AD0, AD1, AD2 up to AD7 look like? Well, an A is always an address. There is nothing else which comes to mind more readily than an address in a microprocessor. And the fact that you have married it with a D means it is a multiplexed address and data bus. Sometimes it is address, sometimes it is data. In alternate cycles, it is address and data, address and data. But some of these, right, are address and data, and some of these are only address. Right? Like from A0, A8, A10, A11 up to A15. So from A0 to A15, you have 16 address pins, and AD0 to AD7, you have 8 data pins. So that's very clear. We are almost 75% through the IC, and we have sort of understood what it's doing, right? VSS. VSS is electrical engineering speak for ground. VCC is electrical engineering for plus 5 volts. VSS is for ground, 0 volts, and always VDD stands for minus something, right? So VCC, then your mind should say plus 5, or plus 10, or plus 9, or plus 6. VSS 0, 0, right? VDD minus. So this is understood. You have to also understand it. Okay? Then we see S0. So let's put it aside for some time. S1, put it aside for some time. RD sounds like read, WR sounds like write. IO and M bar, we have met it in some previous class to choose the memory and the peripheral space. Right? Ready, reset, clock out, hold acknowledge. Right? Okay. I'm not sure what hold will do. Maybe it holds something. Right? Like we say, can I put you on hold? Right? Maybe it's something like that. Maybe putting a 1 on this pin actually suspends this microprocessor and does not allow the clocks to go high and low. So the microprocessor just stays. It's like saying statue to the microprocessor. So hold, it must be like that. And if I put a hold, the microprocessor will say, okay, I'm in statue mode through the hold acknowledge. Maybe it's like that, maybe it's a correction, because when you are reading the data sheet, nobody expects that you will understand all of this in the first page itself. You can go forward, read, and come back again. Right? Now, this particular dual inline package chip of 40 pins is given in a block schematic here. So the internals of this chip are given here. And if you look at this, you should not say, my God, if they ask this diagram in the exam, what will I do? Life is not about exams. Right? Life is about using this in a project of your own. So let your eye wander to the left and look at this breakout diagram of what is inside this chip. Right? Let your eye go there. Look at this. Don't get afraid. Right? Look at what he's saying there. Right? For instance, now, when you look at the pins you did not understand here, you say that, okay, he's now explaining that these two pins, reset out and reset in, are something to do with reset, right? Something to do with control and timing. Now, X1, X2 is a clock, and clock generator is on clock out. So this is an output clock, this is an input to the chip. Good. Read, write are read and write. Then let us go out, because these are all the insides of the chip. Right? It tells you there is a register B, register C, register D, E, H, L. Right? You know what H and L does. Right? All of these you know. Right? Let's look at the interrupts, because that's what we are looking at. And in the interrupt, you will see there is a trap, there is a RST 7.5, there is a RST 6.5, RST 5.5, interrupt acknowledge, and inter. So these set of pins, which I can see here, trap, RST, 6.5, 5.5, interrupt, inter, are the interrupt pins. Now, I don't know which of these is the pin specific interrupt. That I will read and find out. But it looks as if interrupt and inter are not pin specific. If there is something called device telling the microprocessor what to do, probably the device will say this through this interrupt pin, because this seems to be something special. So we'll see whether it's special. What is trap? Okay, we read about non-maskable interrupts, that a interrupt which cannot be stopped from happening. Maybe this trap is a non-maskable interrupt, but I don't know. We'll go forward and read it, and we'll come back and say, oh yes, trap was an NMI. So we'll go forward. Right? Then each pin is described. Once again, don't ask your instructor, sir, is this coming in the exam? Is this table you're going to ask something? It doesn't matter, because in your professional life, Professor Dogra and I have very little contribution after you go out of course, or go out of IIT. So you will please read this and try to understand. It may look difficult, but it is not that difficult at all. For instance, easy to understand. A to A15 is pure address bus. AD0 to AD7, multiplexed address data bus. ALE, address latch enable. And there's an explanation. Right? It occurs during the first clock state of a machine cycle, enables the address to get latched into the on-chip latch of peripherals. The falling edge of the address latch enable guarantees. When you read this, don't say, Patani, something is saying here. Don't try to understand. No, think, what is he saying? What is this fellow saying? He's saying that, okay, these buses are meant for address and for data. For a short time, you'll have the address on them, but then the address will go away and the data pins will start appearing on the same pins. Right? So let us latch the address. So you need the address latch enabled to lock the address into place so that it doesn't go away when the data possesses the bus. So that's what it says. So nothing in this is actually very difficult. So let's go ahead and go to the interrupt part, because we are talking about only the interrupt part. Right? But I am skipping ahead because my interest is to tell you about interrupts. But you shouldn't skip ahead. You should read all of these. Right? You may actually discover something very interesting, like hold. Hold indicates that another master is requesting the use of a address and data bus, which means that more than one microprocessor can be there in a system, and one microprocessor can tell the second microprocessor, you hold, I am going to take control. So this is the pin for doing that. Similarly, that microprocessor will say, yes, I am now on hold, you can now use the bus. That's the hold acknowledge. Very useful pins, but you should not skip ahead, read them. Now, let's go back to that. See how I am going back. It's not that I have seen this data sheet for now 30 years. It's not that I know everything about it. I will also go back and forth. That is why we have data sheets. Right? No shame in that. And we said this must be an interrupt pin, INTR. This must be an interrupt acknowledge. Now we are going to look at that interrupt acknowledge and interrupt pin, the interrupt request. INTR is interrupt request. It's a general purpose interrupt. If it is active, program counter will be inhibited from incrementing, and an interrupt acknowledge will be issued. During this cycle, a restart or a call can be inserted to jump to the interrupt service routine. So now, since I did all this so many years back, 36 years back, right? I don't remember restart and call. So what do I do? So what I do is, I say, what is the restart instruction in 8085? So that's what I do. So it says it's a 1 byte instruction. Okay, I open something. So it is a 1 byte instruction, and this is not a very readable thing, right? But it is equivalent to a call instruction. So I somewhere saw this. It's a 1 byte instruction, functionally same as call this, right? So it means call and restart are same. Right? Let me look at what is a call instruction. What is a call instruction in 8085? So the call instruction is an instruction which transfers the program sequence, the sequence of instructions, the program sequence of those instructions to the operand, to the memory address in the operand. So if I say call and a 16-byte address, the next thing which will happen is execution will jump to that 16-byte address and it will start executing from there. So suppose I look at what Geeks for Geeks is saying. Let's look at, so jump, call, return. We are not interested in jump. Let's look at call. What is the call instruction? So call address unconditionally calls this address. So if you say call 2050, it will unconditionally jump to the address 2050. It will not ask you, why are you asking me to jump? Isn't this a wonderful instruction? Isn't this exactly the type of thing you want to handle your interrupt service routine? That you should be able to say call and the first address of the interrupt service routine, and without asking you any questions, right, the processor will just jump there and do whatever is placed at 2050. Isn't that exactly what you wanted for your interrupt service routine? Yes or no? What happened? Did everybody fall asleep?
Yes, sir.
Yes, this is the instruction you have been waiting for, that somebody will tell you about this. So the call instruction transfers the program sequence to the memory address given in the operand. Before transferring, the address of the next instruction after call is pushed onto the stack. Call instructions are of two types, unconditional call and conditional call. Now, do we want conditional calls for the ISR or unconditional calls?
Unconditional.
Unconditional. So we don't want, we don't know whether we are coming back. We say bye-bye, aloha, and go away. Right? The returning instructions we will embed in the interrupt handler. So we are not going to say that if Sushant is a good mood and he is wearing a lungi, then he will go and bring the milk. We don't say things like that. We say go get the milk. Fine. So unconditional call is exactly what we want. And when you execute this opcode, what happens is somebody must give you on the data bus the 2050, right? Whether you get it from memory, whether you tell it by hand, whether you read it from a device, if you get that 2050 on the data bus after issuing the call, it will go to the 2050. Now, if you put 2060 on the data bus, right? And how many data pins are there on this data bus? D0 to D7. Only eight bits. So you cannot transfer this 16-bit address directly. So you can first transfer this 20, then transfer this 50. So you will have to have two transactions on the data bus to first transfer this 20, then transfer this 50. So that means if I issue a call, even if I embed the call instruction as part of a assembly code language, and then I somehow place 20 on the data bus, and then in the next cycle I place 50 on the data bus, the microprocessor will go to 2050. Wonderful. That's exactly what we wanted. So let's let's go back, right? Go back and say where we were. Okay, so let's go back and say that we will execute. Oh no, we were not here. We were in the data sheet. So during the cycle, a call instruction can be inserted to jump to the interrupt service routine. So the call is exactly what God should have sent us, and God sent it to us. Next, the interrupt request is enabled and disabled by software. It is disabled by reset, and immediately after an interrupt is accepted. Fine. Then what does an interrupt acknowledge do? Interrupt acknowledge is used instead of read bar during the instruction cycle after an interrupt. It can be used to activate a interrupt port or a interrupt IO chip. We will talk about 8259. So just remember that the int acknowledge is to the device which is interrupting. Then what then were these pins? There were these pins which we didn't understand, RST 7.5, 6.5, 5.5. We said, okay, we'll come back to this. We also didn't quite understand trap. He said, we'll come back to it. Right? So let's go back and see what he says about RST 7.5. Now, if you look at RST 5.5, 6.5, 7.5, these are all inputs. You can see type inputs. Now, these inputs have the same timing as interrupt request, except that they cause an internal restart to be automatically inserted. So the restart is like a call, but it is internal, right? So the call can be an external call. Externally, the call 2050, the 20 and the 50 can come from outside on the data bus. But when you have a restart, it's like issuing a call, but the 2050 is internally generated. Oh, that's wonderful, because then you can actually say restart, right, with an address, depending on whether it's 5.5, 6.5, 7.5, and it will jump to that address. And say, okay, so these three things are like that thief is knocking at the window, therefore give the house keys. So thief is knocking at the window 5.5, therefore restart with this particular address which is tied to RST 5.5 and do something. The priority of these interrupts is shown in table 2. Oh, that means they have a priority. Right? 5.5 is higher or 7.5 is higher. Let's go to table 2 and find out. Right? So in table 2, the highest priority is trap. Oh, so we learn that trap is a high priority interrupt. Fine. It may be the NMI. We haven't learned that yet, but it could be the NMI. And the address to which it branches when interrupt occurs is 24H. RST 7.5, priority 2, priority 3, priority 4, and priority 5. Right? And in interrupt, the general interrupt, which looked like the most useful pin, there is a note 2. So let's read the note 2. The address, this is note 2. The address branch 2 depends, okay. The address branch 2 depends on the instruction provided to the CPU when the interrupt is acknowledged. So where you go to will depend on the device which is interrupting you. So we will learn how that device which is interrupting us will give that instruction, right? So we will learn that. Let's go back now. Do you see how this data sheet, right, is a back and forth thing? You will never be able to read it from beginning to end and then answer exam questions. Because in real life, we don't answer exam questions. We design systems, right? So never read a data sheet as if it was for an exam. It is not for an exam. It is to understand how to use this, right? So let's go forward. We seem to have exhausted all the interrupts related lines except trap. Trap is also an interrupt. We have a vague suspicion that this is the NMI which we wanted to confirm, and we confirm it here. Trap interrupt is a non-maskable restart interrupt. Now restart, I said, is a call with the address coming from inside. A call is a restart with the address coming from outside. So it's a non-maskable restart. So it is recognized as the same at the same time as INTR or RST 5.5 to 7.5. It is unaffected by any mask or interrupt enable. It has the highest priority of any interrupt. So this is the NMI. So if you want to know where is the NMI, you can say NMI trap, right? So NMI trap. So now we understand more or less that when we attach a device to 5.5, the device on 5.5 will go to a specific address, which is equivalent to saying restart that address. The device on 6.5 will go to a specific address, which is equivalent to saying restart that second address. By the way, are you all with me? Or have I lost you along the way?
Sir, I'm with you, sir.
Yes, sir.
Sure.
Great. Just hold on. I'll go back to my presentation and say, now let's look at the trap, right? Which is RST 4.5. We don't call it RST 4.5. We call it trap, but it is RST 4.5. And if you take this number 4.5, the interrupt number into 8 is the vector address. So let's take 4.5, multiply it into 8, you get 36, decimal 36, which is 24 hexadecimal. How do I do that? How do I get that? Oh, well, I'm lazy, right? I say, okay, what is 36 decimal in hexadecimal? Fine. Okay, so 36 decimal is 24H. So that's how we get this 24H. That's cool, right? You don't have to bust your brains trying to convert 36 decimal into 24H. Just say ask Google, right? I mean, that was not the way I did it so many years back, but today I think I find this more easy, right? So please use these tools. These are easy tools to use. Similarly, you can calculate 5.5 into 8 is how much decimal it will come out to 2CH. The same thing, right, for software interrupts, right? Software interrupts are interrupts which you give from the software. You will find RST5 means 5 into 8, 40. 40 decimal is 28 hex, so it is 28H. Right? These are software interrupts, right? So you can have hardware interrupts, you can have software interrupts. INTR is the only non-vector interrupt in the 8085. Now, if we go forward, there can be interrupt nesting. That's a complication. Right? So the one interrupt arrives while we are servicing another, so that's a complication. So one way of solving this is have priority interrupts. The interrupt 1 has a higher priority than interrupt 2. So if they come together, we will always take interrupt 1 and not take interrupt 2. What we will do with interrupt 2 is another question. Whether we will buffer it and take it later after we finish, or we'll just drop it is another question that we will not deal with now. Right? The thing is other simultaneous interrupts. What will happen if interrupts come from 2 or more devices at the same time? Now, what do? Same time means you have to deal with them together. So what the processor does is to say that, okay, if this device comes, I will always take it first. So it is inherently prioritized by placing a bit in a interrupt request register. So doesn't that destroy the simultaneousness? Right? It does, but there is no other way of dealing with it because your processor is a sequential device. It can only do one thing at a time. So you must prioritize. And this is one way of prioritizing, right? So it's like two people shove their hands into a ticket counter saying, movie ticket chahiye. Now you have two hands in front of you. Which hand do you put the movie ticket in? So what you do is you write token 1, token 2, and into one of the hands you always say this is token 1, right? And this is token 2. Now you say, withdraw your hands and see, are you token 1? Then I'll service you first. Are you token 2? I'll service you next. You see, you have broken the time deadlock. Both of them had put their hands into the window at the same time by actually giving them a token tiebreaker. You destroyed that simultaneousness by giving them that token. And here what we do usually in processors is, even if you arrive at the same time, we just say that, okay, no, this is the first one I'll do, second is this one, always, right? So let's go forward and see what priority interrupts are. I'm worried that when I say, "Are you with me?" only a few voices say they are with me. It's like a general goes into battle and there are only 2 soldiers behind him. That's not much of an army. Are you?
To be with you.
One voice says, "We are with you."
Sir.
All right, let me assume that all of you are with me and you have not actually lost the thread. But okay.
Sir,
yeah.
Sir, can you once again explain the non-vectored in 8085, the INTR?
The INTR will first say that I want service, and then it is the responsibility of the device requesting service to put an address of where its interrupt handler is. So after you raise the INTR high, the subsequent thing you must do is to place the 16 bits of data of address on the bus so that it knows where it has to go to. That responsibility is the responsibility of the device making the interrupt, because the processor has no particular vector information about that. So we will just see how that will happen in a short while, maybe 2 or 3 slides from now, right? But it's going to come from the device. That's the difference. It will first raise the interrupt request, then it will say, this is the address to which you should go. Right? Just like the milkman first interrupted at the door and then told you, go to the kitchen rack number 2 and get that milk vessel. I will pour my milk into that. So the responsibility for saying that, get that vessel, was the milkman's responsibility from outside. You didn't know. Fine. So that is what happens. The interrupting device will now push two successive bytes of information into the data bus, and those are the 2 bytes which the processor will use to jump to where the interrupt handler is expected to be. Right? Now, if you don't have an interrupt handler there, you have a problem. So you better place an interrupt handler at that location and then have the device jumping to that location. That's your lookout as a programmer. Is that okay?
Yes, sir. So like automatically will check the address where it will go once the
address will come from the device interrupting. The device which is interrupting will give the address to which it should go. That's the difference. The address will come from outside.
Okay, sir.
Now, prioritized interrupt. First of all the IO devices must be organized in a. Was there a question?
Yes, sir. One doubt.
Yeah.
Sir, can you go to slide number 37, please?
37, okay.
Sir, when RST, suppose that RST 5.5 pin is on, so what will happen that the current contents of PC will be saved in a stack, and PC will be loaded with that 2CH address, and and after that ISR complete, the stack, the address from the stack
will be popped. Will be popped
Sir,
back.
But one doubt is that why is it called restart?
Oh, it's called restart because the instruction opcode is restart. I told you that there are 2 instructions which transfer unconditionally the execution sequence. One is a call, the other is a restart. Fine. The restart, the address comes from within. The call, the address comes from without, if I can use that word. Apart from that, there is no other difference between the call and the restart. Both of them will place the instruction, call will place the instruction of the next instruction into the stack and then go to that execution address. That's the difference. And this you have to handle it yourself. Right? There is no other difference. It so happens that in the 8085, that is what is the name of the opcode. So what is the restart instruction in 8085? So if you look at what is the restart instruction, you will find that, okay, I should look for Intel's explanation, but somewhere in this you will find that the restart just expects a memory address to which it can transfer execution. That is all. Fine.
Okay, sir. Like it is just pin, and we are not explicitly giving the address. That's why it is like.
No, it is a vector address. It will, whenever you have the interrupt coming on RST 5.5, it will execute restart 24C. Sorry, not 24C, 2C. Restart 2C. This 2C will come from inside. It will not be put on the bus by an external device. Right? That's the only difference.
Okay, sir.
In the inter, the address is not specified. It will come from outside. It has to come from outside. Right? We'll see how it will come. Right? We'll see how it will come. It's not that I'm stopping here. We'll see how it will come. So what is the priority interrupt? A interrupt. So there is a hierarchy in the I/O devices. Some I/O devices have a higher priority structure than the other devices. So if you have a high priority device, that interrupt will be accepted, right? If you are already executing something from a lower priority and a higher priority comes in, you will go and interrupt, service that higher priority interrupt, but not vice versa. If you are servicing something higher and a low priority comes, you will not service it. So multiple level priority means that interrupt requests will be accepted from some devices, but not from others, depending upon the device's priority, right? To implement this scheme, we can assign a priority level, let me make this a little bigger, to the processor that can be changed under program control, right? And then nested interrupts then become simpler to handle. Because nesting, therefore, is a question of determining whether what came is a lower priority or a higher priority. Lower priority, I ignore. Higher priority, I service. Right? Then what we do is we say, how do we control the I/O device behavior? So we need some mechanism in the individual I/O device to control whether a device is allowed to interrupt the processor or not. So if I don't want it to interrupt the processor, I will go to that I/O device and in the status, in the interface circuit, the status register, I will set the interrupt enable bit. If I set it, then it can interrupt. If I unset it or reset it, it cannot interrupt. So you can use this power over an I/O device, even whether it's simple or complex. You can actually control it from the processor side. If you don't want a keyboard to contribute a character during something, go to the keyboard, set its IE to 0, and then it cannot send any interrupt, even if somebody presses the key, right? So this is quite possible. Now, how would we control the I/O behavior in our keyboard and display devices? Right? First, look at this. Look at this. 4 processes control registers. Right? So we need a status register in the processor. One possibility is there are 4 processor control registers. One is PS, one is IPS, one is I enable, one is I pending. So if I look at the status register, let me just break this up. Status register, then IPS, then I enable and I pending. So the process status register includes the IE and the processor will accept interrupts only when this is set to 1. Right? So this IE bit, if you set it to 1, then the processor will take interrupts from this device. What is the IPS? The IPS saves the content of the PS when the ISR starts. So when the ISR starts, this orange arrow means whatever is there in the PS is saved into the IPS. Because when you come back, the IPS will be saved back into the PS. Right? So this is why you need an interim register where you store the status of the PS when you go and handle the interrupt. Now, since there is only one register available for storing the status information, it is necessary to save the contents of IPS on the stack if nested interrupts are allowed. So if you have more than one nesting, then this IPS must be pushed onto the stack, popped from the stack, and that you must do for all the nestings you encounter. The interrupt enable register, that's the third register, right, in the keyboard, allows the processor to selectively respond to individual I/O devices. Now, a bit may be assigned for each device, as shown in the figure, for a keyboard, for a display, and a timer. And when a bit is set to 1, the processor will accept interrupt requests from the corresponding device. So if your keyboard is set to 1, then it will accept from the keyboard. If it says to 0, it will not accept from the keyboard. I pending register indicates active requests, active interrupt requests. So if multiple devices raise a request, then a program can decide which interrupt should be serviced first. Right? So this is used for establishing that priority. Right? Now, you can use this mechanism for establishing a priority, right? And these registers are special. So you have to use special instructions to do things with these registers, not general purpose, of course. Right? But once that is allowed, this is a good way of establishing a sort of rudimentary priority among interrupting devices. Now, examples of interrupts. For instance, let us read a line of characters typed on a keyboard. Right? So we will use interrupts with the keyboard, but we will not use interrupts with the display, because displays are always ready to display. So they will not interrupt the processor. So the processor, whenever it has something, can always display it. So we do not think that interrupts are necessary with the display. So we poll the display, but we do need interrupts with the keyboard. Right? Now, if you go forward, right? If you go forward, you will see that there is an example in your book which says this is the code for getting an interrupt based key from the keyboard and writing a character to the display. So I would suggest that you go through that code. I have not replicated the code here because it's there in the textbook, and please go through the code and you will see that it establishes two clear routines, one for getting an interrupt based key pressed on the keyboard and the other for getting a displaying a character to the display. Right? Now, can we stop here and take some questions? If you have used a 8085 simulator, most of these things you can actually do on the simulator. Fine. So if you have an 8085 simulator, and there are many on the net, on the internet, I don't remember, but I'm certain that you're already using some simulator. Yeah, so Zim 8085, for instance. Okay. You can use this simulators. How good these are, Professor Dogra will be able to tell you, right? But I'm certain that they'll be doing most of the things you need for them. Right? Is that okay? In the classes to come, maybe tomorrow is the next class, I will be talking about one interrupt controller called 8259. Right? So I will be talking about this. So 8259 is the interrupt controller we will look at. Specifically, the data sheet is here, 82C59 from Renesas. So just you can go to Renesas 8259 and see what it does. We will discuss this in the class tomorrow. Okay. Okay, so I'll stop here and you can go to the other lecture which is scheduled, and we will take it up tomorrow at 9 o'clock. Is that okay?
Okay, sir.
Right. Do you have any Diwali related issues in attendance? For instance, all my class students have actively developed illnesses, dead grandfathers, married cousins, all around 3rd, 4th, 5th of November. So any such problems from your side? Any Diwali related attendance issues, because I am already hearing bargains from my class saying, why don't you take 2 classes on one day and leave us on 5th? I hope you don't have any problems like that.
So can you do that?
Well, I'm supposed to take a class on 3rd and then a class on 5th. 4th, I don't have a class. The Thursday afternoon class is on Diwali. I'm not taking a class, but I do have a class on 3rd morning 9 to 10, 5th morning 9 to 10.
Sir, we can schedule the 5th class later on.
Yes, sir.
So 3rd is possible for you, Wednesday?
Yes, sir. 3rd is possible.
Yeah, my only thing is my class is, yes, 3rd is possible for me. Wednesday is possible. Both are possible for me. We don't have anything called Diwali in Delhi. Not anymore.
Achha, not anymore. I thought that Delhi is famous for Diwali only.
Absolutely. First of all, firecrackers are banned. Secondly, mixing is banned.
Yeah, that's correct.
You don't go anywhere.
But sweet distribution is not banned. Distributing
No,
sweets.
you can't go to anybody and distribute sweets.
Oh, is it like that?
Yeah.
Oh, okay.
There is nothing to do except light one diya and
even spending time with family is also there.
Yeah, that I've been doing for 2 years now.
So if you
That is
allow them Wednesday we can have 2 hours and then we can cancel Friday's class and we'll shift it to the next week.
We don't know. Actually, my class is bargaining for 2 hours on Wednesday. So
Okay.
Alternate. I will take 2 hours for them.
Okay, alternate. Okay.
Well,
Then we will shift the class next week. No issue.
that last class which we were supposed to have, that 10th, I think 10th November.
Wednesday. Yeah, next Wednesday.
That we can have 2 hours.
Yes.
Yeah. Okay. That's also possible.
So then next Wednesday I can come for a couple of hours. Okay. Next just pre-Diwali days. Okay.
Okay. So do I take the pre-Diwali class? I do.
No. I will take that pre-Diwali class Wednesday 9 to 11. Okay, you carry on with your own class at Delhi. Okay. Next Wednesday, you can take a couple of hours lecture if you are.
Yeah, next Wednesday will be, our semester would have ended by then. 7th November we are ending.
Okay.
Yes, next Wednesday, 3rd, 4th. Next Wednesday is 10th. Yeah, 10th.
10th. So 10th, I have scheduled one class. You can take 2 hours class there.
Fine. All right. Instead of 5th, I'll take 2 hours on 10th.
5th, are you going to take 5th?
No, I won't take 5th then.
Okay, so then Wednesday and 3rd and 5th classes let me take. Okay.
Yeah. All right. Okay.
That's fine.
But if I do that, then I'm taking one class less, right?
After 10th also we have now. You can take on 11th also.
Our exams will start then. Then the catch is, let me take 5th one class and 10th 2 hours.
That will be sufficient.
Yeah.
Okay.
Let me take 5th one class only and 10th 2 hours.
Okay, sir. Okay.
All right.
Okay.
Right.
Okay.
Bye-bye.
Okay. Thank you, sir. Bye-bye.
Thank you, sir.
Bye.
Thank you, sir.
Okay, thank you, students. Please join today's lecture of Professor Manindra Agarwal. He is, he was my teacher at IIT Kanpur, and he is one of the, best professors in, cryptography and modern cryptography things. So you must enjoy his lecture. Okay. I'm sure that you will enjoy his lectures. All of you, please join that seminar. Okay, thank you.
Thank you.
Thank you, sir.